Yeah, I will share the screen now. And we'll start at 2:30. Not at 2:30, we will start at 3. Okay, so it is 2:59 and 3 o'clock we should be going. Okay, so it's 3 o'clock. I think we can go ahead and start. So today we'll be doing Compton Effect and X-ray diffraction. Let's see if we're able to complete both of them, or we are right now on slide number 13. We have to go up till slide number 48. So we have 2 more lectures left today and tomorrow, so I hope that we'll be able to finish everything by then. We have quiz on Wednesday. Okay, and then I would want to leave you all to study for the last week to prepare for the final exams, because as you all know, our final exam is on 8th of January, right? Have you all got the date sheet?
Yes, ma'am. Yes.
8th of January को है ना हमारा final exam. Okay, so let's start with Compton Effect. And so our chapter is particle properties of waves, and Compton Effect is basically about the scattering of X-ray. Basically, if we have an X-ray photon that strikes an electron, okay, what's going to happen to the X-ray photon? The electron is scattered away. The electron receives an impulse and begins to move, okay? And the X-ray photon is scattered away from its original direction. Like if you have a diagram that looks like this, okay? If we've been talking about particle properties of waves basically, and we are interested in the scattering of X-rays when it strikes an electron, okay? So basically this tells us about particle nature of the photon. Why is it significant for us? Is because it tells us about the particle nature of the light. The quantum theory of light is like that photons behave like particles, except for their lack of rest mass, okay? Photons obviously do not have mass, they're massless particles, but they behave like particles. And X-ray and Compton effect is one of the effects that explains the particle properties of light. Okay? So for example, if you have an incident photon like an X-ray wave, okay, and this is an electron over here, and the X-ray photon is going to, when it hits the electron, the X-ray photon will be scattered along a different direction. We call that phi, and the electron will gain some momentum, and initially the electron was at rest. It gained some momentum, and then the electron was pushed along. It takes on a different path. It gains some velocity due to some energy that it gained from this some of the energy it gained from this incident photon, and then it's scattered along this direction, theta. So what we want to do here is we want to derive an equation basically for, let me show you what equation. We want to derive an equation for lambda dash minus lambda. ये हम equation derive करना चाहते हैं. This is the Compton effect. This is the formula for Compton effect basically, कि जो हमारे पास पहले lambda था X-rays के original wavelength, then due to the scattering of the X-rays, they will lose some energy, and basically if the original energy was E is equals to h nu, then it will lose some energy, and its wavelength, its frequency is going to decrease. Okay, it will lose some energy. Basically इसके यहाँ पे it will get its final energy will be E is equals to h nu dash. So what we want to do is we want to find a formula for lambda dash minus lambda, and that is equal to h over mc 1 minus cos phi. Basically we're going to derive this formula today. That is the Compton effect formula. Okay, so what we're doing is that what our scenario is that there's a collision taking place with an X-ray photon. It strikes an electron, okay? and the electron is initially at rest in the laboratory coordinate system, and the electron is scattered away from its original. The photon is scattered when after it collides with the electron, is scattered away from its original direction of motion, while the electron receives an impulse and begins to move. Okay, so the electron will get some impulse and will begin to move. Initially, the electron was at rest. So we can think of the photon as losing an amount of energy in the collision. Okay? So basically, what the condition that we will have over here, we will start with, is that the loss in the photon energy is equals to gain in the electron energy. So the loss in the photon energy is h nu, which was its original initial frequency, minus h nu dash, which was its nu dash is its final frequency, and nu is its original frequency. So this is the amount by which the photon has lost energy, and that is equal to the gain in the electron energy, which comes as the kinetic energy of the electron. Okay? So now let's see. Now loss in photon energy is gain in electron energy. This is the same equation as before. And now let me open the whiteboard. ठीक है, so basically
Excuse me मैम.
yes
मैम ये जब फोटोन जो है ये जब इंटरेक्ट कर रहा है इलेक्ट्रॉन के साथ और फिर इलेक्ट्रॉन एनर्जी एब्जॉर्ब कर रहा है, तो इलेक्ट्रॉन कोई हमेशा स्पेसिफिक एनर्जी एब्जॉर्ब करता है ना, तो ये डिपेंड करता है ना कि वो मटेरियल कौन सा है, वो एलिमेंट कौन सा है जिसका ये इलेक्ट्रॉन है.
नहीं, we're not talking about orbital levels here. Here it's just a plain electron, not associated with any atom.
Okay.
This is not yeah. ठीक है, we're just talking about a collision between an X-ray photon and an electron. ठीक है? So when we knew that we have the relativistic formula, and here we're going to apply relativity as well. ठीक है? So if we have E squared, we know that we had in relativity m square c squared plus p square, no, this is c power 4 plus p square c square, right? You all remember this formula from relativity? Now for the photon, the mass is 0, right? So basically for a photon, we will have E is equals to pc. This formula applies for a photon. Why? Because this term goes to 0. And we have E is equals to E square is equals to P square C square. If you take the square root of both sides, you will get E is equals to PC. So this equation applies here. Now, if the energy of a photon is h nu, so its momentum, this is the equation that relates the momentum of a photon. The momentum of a massless particle is related to energy by this formula. Okay? E is equals to Pc. So the energy of a photon is h nu, so its momentum will be E over c, and if you put h nu for E, you will get P is equals to h nu over c. Okay? And this is the diagram. Now if we look at this diagram over here, this is the incident photon. Okay? This is the scattered photon, and this is the scattered photon, and this is the scattered electron. So now, before, if we use conservation of energy, what this photon initially had E is equals to h nu energy, and then final energy is E is equals to h nu dash, where nu dash is the final frequency and nu is the initial frequency. Okay? Its initial momentum is h nu over c, as we just found out over here. H nu over c is its initial momentum. Oops. And then h nu dash over c is its final momentum. Then we also, when we have to consider the conservation of momentum, we'll be considering these angles as well, because we'll be taking the momentum along the y direction. This momentum in the y direction, its component will balance the component of this along the negative y direction. Then we have to add their momenta along the x direction, and we'll see, and we have to consider this momentum as well. Okay? Initial plus the final momentum should be equal to, should be conserved. Okay? So let's see how we're going to do this now. So initially, we understood what the initial energy of the initial photon is and the energy of the final photon. In terms of momentum, we can also get that equation. We got that equation. And then for the electron, initially it was at rest, so it will only have a rest mass energy, which is E is mc square. Its momentum will initially be 0 because it's at rest. Then when this electron is being scattered, its momentum will be called that momentum P. Its energy will be defined as square root m square c square plus p square c power 4. And we are considering relativistic. We are considering the effect of relativity over here as well. Because obviously the incident photon is moving with the speed of light, so it's so we have to use relativity here. So I'll come to this diagram in a moment. Like if you can see the components. If this is our p vector here for the scattered photon, which is h nu dash over c, then this we have to consider its components in the right along its x direction component will be h nu dash over c cos phi, and its y component will be h nu dash over c sine phi. Similarly, if we take components of this as well, this the momentum of the electron. To get momentum of the electron, we have theta over here, so it will be this direction along the x direction. The component will be p cos theta, and then along the y direction it will be p sine theta. So momentum is a vector quantity that incorporates direction as well as magnitude. And in the collision, momentum must be conserved in each of those two directions. Okay? So we have to conserve momentum in each of the y direction as well as the x direction. So we have to apply conservation of momentum. We'll get two equations, one from the conservation of momentum in the y direction and one from the conservation of momentum in the x direction. So the directions we choose here are that of the original photon and one perpendicular to the plane. So original photon was coming along the x direction. We will consider that as one direction and the other one perpendicular to this one, which is the y direction. So now let's see what we will do here. So the initial photon momentum is h nu over c, okay? The scattered photon momentum is h nu dash over c. And the initial and final electron momenta are 0 and p. As you can see over here, initial momentum of the electron is 0 because it was at rest, and the final momentum is p. So according to along the original photon direction, which is the x direction, the initial momentum is equal to the final momentum due to conservation laws. Conservation of momentum will say that the initial momentum is equal to the final momentum. So the initial momentum we have along the x direction is only h nu over c, and the final one, it will be h nu dash over c cos phi, h nu dash over c cos phi plus p cos theta, because it's along the x direction, plus p cos theta. So ये हमारे पास एक equation आ गई है. And perpendicular to this direction now, perpendicular में हमारे पास क्या आएगा? We initially along the y direction there was no momentum because initially this was at rest and this was moving entirely in the x direction. So we don't have, so the initial momentum is 0. Initial momentum is 0. And then along the y direction, this will have a momentum h nu dash over c sine phi, okay, minus p sine theta, because this is in the negative y direction. Minus p sine theta. So ये हमारे पास एक और equation आ गई है. ये समझ में आ रहा है सबको कि ये दो equations हमारे पास किस तरह आई है? Conservation of momentum हमने apply किया है और इस diagram को हमने use किया है. So basically now, the angle phi is the angle between the directions of the initial is between the phi angle here. It is between the initial photon's direction and the scattered photon's direction. And the theta is between the directions of the initial photon and the recoil electron. Between the initial photon's direction and the recoil electron's direction is the angle theta. So now what we're doing is that we can find a formula that relates the wavelength difference between the initial and scattered photons with the angle phi between their directions. What we want to do in this Compton effect is we want to find out the difference between the lambda, the two wavelengths, this photon and this photon will have some change. There will be some change in the wavelength of these two photons because it loses some energy. So we want to find out how much of that wavelength, we want to relate that wavelength to this theta, to this, not theta, to this phi. We want to relate it to the phi, which is the change in which is the angle between their directions. between the directions of the initial and the scattered photon. That is what we're trying to do here. So we have these two equations, this equation here, and we have this equation here. Now what we're going to do, basically phi is a measure, which is a measurable quantity. Unlike the energy and momentum of the recoil electron, ठीक है? Energy and momentum of the electron हम measure नहीं इतना आसानी से कर सकते, ठीक है? But phi, which is the change in the angle between the change is the angle between the two directions of the scattered and the initial photon. That is possibly measurable, ठीक है? Like if you place the detector somewhere over here, then you can determine if this is along this direction. You can determine that there's a X-rays being appeared over here, okay? You can detect the extra photons over here. So then you can measure this angle. So it's measurable. So that's how you can determine the change in the wavelength of the photons. So basically now the first step we have to do is take these two equations. First step is to multiply equation 2.16 and 2.17 by C, ठीक है? ये जो हमारे पास ये equation आई है और ये equation आई है, इन दोनों को C से multiply कर दें throughout. So what we get now is this will be h nu is equals to h nu dash cos phi plus pc cos theta. ये cos phi, ये आ गया हमारे पास पहला equation. pc, wait a minute. Yeah, they just wrote this part first, ठीक है? pc cos theta is equals to h nu minus h nu dash cos phi. That's how they wrote it over here, ठीक है? And then the second equation, which will be pc sine theta, is equals to h nu dash sine phi. ठीक है? ये दोनों equations हमारे पास इस तरह से आई हैं कि हमने इस equation को और इस equation को c से multiply करके make pc times cos or sine theta the subject of the equation. ठीक है? Now what we're going to do, we're going to square. As you can see, the theta can be easily eliminated if we square both the two equations, and then we add them. Squaring each of these equations and adding the new ones, obviously we're going to get rid of theta because sine square theta plus cos square theta is 1. ठीक है? So when we square the two equations and we square the two equations, ठीक है, and add the new ones जो हमारे पास square करके equations आएंगे दोनों, उनको add कर दें, then the angle theta is eliminated. We'll basically get p square c square is equals to h nu whole square minus 2 h nu dash cos phi plus h nu dash whole square. And this you should verify this on your own, ठीक है? Like I have done this before, but it'll take too much time if I write this on the board, ठीक है? It's just basic algebra, ठीक है? You just have to square these two equations and add them, and those two will cancel out. They won't cancel, but these two will add to 1, ठीक है? So we'll get p square c square, and then you have to do this whole square of this and whole square of this, ठीक है? And then you will get basically this equation. ठीक है? So it's not very difficult. You should be able to do this on your own. So next we equate the two expressions for the two total energy. Now we have used already हमारे जो equations आए हैं वो conservation of momentum से आए हैं. Now what we want to do is we want to apply conservation of energy as well. ठीक है? We'll be able to obtain some one or two. We'll be able to obtain some equation based on conservation of energy as well. We have used so far conservation of momentum to obtain two equations, and then finally we obtain this equation. So now we equate the two expressions for the total energy of a particle. The total energy of the electron will be kinetic energy plus mc square is the energy of the electron. And we also know relativistically that the energy is given by square root m square c power 4 plus p square c square. So this is for example, like, ठीक है? So we're doing this for the electron. So total energy of a particle, ठीक है? For the particle. So from chapter 1, we got this equation from chapter 1. So we equate these two together because E is equals to this plus E is equals to this, ठीक है? So we put this on, we take this part and put it over here. And then we square it because we want to get rid of the square root, ठीक है? So then we get this equation. P square C square is equals to kinetic energy squared plus 2 mc square times kinetic energy. Because अगर इसको हम expand करें तो we will get kinetic energy squared plus 2 kinetic energy mc squared. mc power 4 आएगा. mc power 4 mc squared, two kinetic energy times mc squared, plus then we'll get m squared c power 4, which will cancel with this term. ठीक है, so हमारे पास ये आ गया है. Now, since we know that kinetic energy is equals to the kinetic energy of the electron is the difference, the kinetic energy of the electron is the difference between the initial photon energy is the difference between the initial photon's energy and the final photon's energy, because the photon has lost some energy to the electron, which goes into its kinetic energy. So basically now, ये हमारे पास RD equation था, right? ये कहाँ से हमारे पास equation आया था? ये वाला equation, ठीक है? ये equation, we have this equation, wait. Substituting this value of p square c square into 2.18, एक minute, p square c square is equals to this whole thing, right? ये फिर या basically ये जो हमारे पास h nu है, यहाँ पे हमारे पास wait a minute, what have they done over here? 2mc square h nu, basically we put this thing for the kinetic energy की जगह हम ये डाल देंगे h nu minus h nu dash, ठीक है? और फिर what we will get is p square c square is equals to h nu minus h nu dash. ये है हमारे पास जो आ जाएगा. Wait a minute, what have they done over here? P square c square is equals to h nu squared minus 2h nu dash cos phi कहाँ चला गया यहाँ पे? Does anyone understand what's happening over here? They've basically just done all the substitutions over here, ठीक है? हमारे पास जितने equations हैं, ये equation था हमारे पास. We have basically p squared c squared is equals to, we have this equation 2.18, ठीक है? इसकी जगह हमने p square c square की जगह हमने ये डाल दिया है, ठीक है? ये terms जिसमें हमने kinetic energy को h nu minus h nu dash डाला है इसमें. So we will get this equation, substituting this value of p square c square into 2.18. Wait a minute. p square c square, हाँ, इसकी जगह हमने ये डाला है, इसकी जगह हमने ये डाला है kinetic energy की जगह, तो हमें ये equation आ गई है, ठीक है? इसको because kinetic energy is being squared over here, we have to square this, and when we square this, we get these three terms, ठीक है? When we expand the square, we will get these three terms. ठीक है, यहाँ पे फिर आ रहा है plus 2mc square kinetic energy, which is 2mc square times this thing. So ये हमारे पास आ गया. Now we will equate 2.19 with 2.18. ठीक है, equate substituting this value of p square c square into 2.18. इसकी जगह हमने ये equation डाल दी, 2.18 और 2.19 को equate कर दिया है. Finally, when you do some algebra, there will be some cancellations of some terms. You will get this equation, and I want you all to basically do all this algebra on your own, okay? Because there's a lot of algebra in this Compton effect, okay? So in order to understand, like, to be able to solve this on your own, you should be able to do all these steps, okay? So I want you on your own to, like, basically work out all this algebra and everything on your own. You don't have to submit it, but as a homework, like, basically for your own knowledge, you should do this on your own. Okay? So now we will obtain this equation 2mc squared times h nu minus h nu dash is equals to this thing. Basically, we have equated this equation with this equation. Okay? So हमने अब ये हमारे पास आ गया है. ठीक है, the relation is simpler when expressed in terms of the wavelength lambda. Now nu की जगह हम lambda में करना चाहते हैं convert. So we will basically divide through this equation, divide this equation by 2h squared c squared. इस equation को हम wavelength के terms में लिखना चाहते हैं. We know that wavelength is equals to what is wavelength in terms of frequency? Wavelength is equals to c divided by nu. ठीक है, divided by nu. ठीक है, so we want to convert this into a form that we can write into wavelength. So we take this equation, we divide throughout by 2h square c square, and we will get this equation. 1 minus cos phi times nu over c times nu dash over c. ये basically यहाँ पे अगर देखें तो 2h square यहाँ से delete हो जाएगा और divided by c square. इससे divide by c हो जाएगा, इससे भी divide by c हो जाएगा, ठीक है? And यहाँ पे भी 2 and h will cancel, and we will get remaining 1h. And if we have left 1c here, we will get c and c here. Because we divide by c squared, so ye c square cancel ho jayega na, and we will get, then we can leave 1c here because we are dividing by c here and dividing by c here as well. Now, as you can see, we said that lambda is equals to c over v, so over nu. So nu over c will be equal to 1 over lambda. Okay? And then lambda dash, nu dash. And then nu over c, nu over c will be equal to 1 over lambda. Okay? Where lambda is the original wavelength of the photon and lambda dash is the final wavelength of the photon. So basically now we have an equation of this form. We will substitute nu over c with 1 over lambda and nu dash over c with 1 over lambda dash. We will get mc over h is equals to 1 over lambda minus 1 over lambda dash is equals to 1 minus cos phi divided by lambda dash. And then if we want to go about working this equation, basically ये equation अगर हम rearrange करें तो we will get the equation 2.21. Basically mc over h. ठीक है, इसको हम लिख सकते हैं, ये term है, इसको हम ऐसे लिख सकते हैं ना, minus lambda divided by lambda dash, ठीक है, is equals to 1 minus cos phi divided by lambda into lambda dash. Obviously, ये जो हम देख रहे हैं कि this whole thing will cancel with this whole thing. So basically, we will get left lambda dash minus lambda is equals to h over mc 1 minus cos phi. Okay, so this is the Compton effect formula, which relates the two wavelengths, the wavelength of the scattered photon minus wavelength of the initial incident photon, with Planck's constant, the mass of the electron here, c speed of light, and the phi angle, which tells you the phi angle which is basically the direction change of the incident photon. So this is our Compton effect formula. Where are we? This is our Compton effect formula, okay? And this was equation 2.21 was derived by Arthur H. Compton in the 1920s by this scientist, okay? He was the first to describe this effect, which is known as the Compton effect, to observe this effect, which is known as the Compton effect. And this gives support to this Compton effect is strong evidence for the quantum theory of radiation, which says that quantum theory of radiation is basically that electromagnetic waves, they are given, their energy is quantized, which is in the form of h nu. So that is like the quantum theory of radiation. Basically, the energy is in packets of the photon consists of packets of energy. Okay, the photon exists in the form of its energy is quantized. Basically, that is the quantum theory of radiation. So equation 2.21 gives the change in the wavelength expected for a photon that is scattered through an angle phi by a particle of rest mass m. Okay? So if the electron has rest mass m, then this is the relation between the Compton effect. This is the relation between the two lambdas. The quantity we can call, ये जो हमारे पास h over mc है, इसको हम lambda c कह देते हैं, which is known as the Compton wavelength. ये जो lambda c is equals to h over mc है, इसको हम Compton wavelength कहते हैं. It gives a scale of the wavelength change of the incident photon. ठीक है, it's basically giving you the scale of the change in the incident change. It's basically telling you the scale of the wavelength change of the incident photon. Basically कि हम कितना order of magnitude को से हम change करें, because obviously if you can see that cos phi is a number that is between 0 and 1, ठीक है? So this will it depends if this is positive or negative, ठीक है? Well, this will just be a number between 0 and 1, or it can be also negative as well, ठीक है? In that case, this is the one that is going to be giving you the order of the magnitude, basically. So you can calculate h over mc for an electron. You can see what order of magnitude that will be. So we notice that the greatest wavelength change possible corresponds to phi is equals to 180 degrees. Because what is the cos phi at 180 degrees? Like if we draw an angle, if we draw a diagram for cos of theta, we have a diagram that looks like this, ठीक है? इसमें से because it's 1 minus cos theta, ठीक है? अगर यहाँ पे 1 होगा तो वो फिर 0 हो जाएगा, 1 होगा तो 0 होगा. यहाँ पे होगा तो क्या उसकी वैल्यू होगी? -1. तो -1 यहाँ पे डालेंगे तो 2 times h over mc हो जाएगा. So that is the greatest possible change in the wavelength that you can get, ठीक है? At phi is equals to 180, the wavelength change will be twice the Compton wavelength, lambda c. Because this factor over here will be 2, so it'll be twice the change, twice the Compton wavelength here. So lambda Compton, if you put in the values for an electron, the mass of an electron here, and if you put it in Planck's constant and see the speed of light, you get lambda Compton is equals 2.426 picometers for an electron. And for other particles, it will be even less. Why? Because other particles, they will have more mass, right? For example, proton has more mass, neutron has more mass than electron. So lambda c would be even smaller because you're dividing by the mass. ठीक है? Owing to the larger rest masses, the maximum wavelength change in the Compton effect is 4.852 picometers. ठीक है? So now let's do an example related to Compton effect. So X-rays of wavelength. Does anyone have any questions related to Compton effect? No? Okay, then we'll do this example. So X-rays of wavelength 10 picometers are scattered from a target. Find the wavelength of the X-rays scattered through 45 degrees. Now we have this equation. ठीक है? Now our phi here is 45 degrees. Phi is 45 degrees. And our lambda c is what we have already calculated, ठीक है? Lambda, if we're talking about, and they are talking about electrons here, ठीक है? Part B says find the maximum wavelength present in the scattered X-rays. Maximum wavelength, ठीक है? And part C says find the maximum kinetic energy of the recoil electrons. So basically here, find the wavelength of the X-rays scattered through 45 degrees. So phi here is 45 degrees, ठीक है? And we want to find, we have the incident wavelength, ठीक है? Which is 10 picometers. And lambda c is what here? Lambda c की value है हमारे पास क्या है? For 2.426 picometers. ठीक है? तो वो हम यहाँ इसमें insert कर देंगे. 1 minus cos 45 is 0.293. तो वो हम lambda c की value डाल देंगे जो हमारे पास यहाँ पे थी, which is 2.426 picometers. So here we will get 10.7 picometers. So basically the change in the wavelength. What is the change in the wavelength? The change in the wavelength is basically 10 picometers minus 10.7 picometers. I mean, they haven't asked for the change in the wavelength. They've just asked for the final wavelength. But if you want to, if they're also asking for the change in the wavelength, then you will do 10.7 minus 10 picometers, which is 0.7 picometers. That will be the change. ठीक है? And then part B, they're asking find the maximum wavelength present in the scattered X-rays. So as we said before, this value is the change in the wavelength is maximum when 1 minus cos phi is equals to 2 at phi is equals to 180 degrees. In which case we will have lambda dash is equals to lambda plus 2 lambda c Compton plus 2 times the Compton wavelength. So that will be 10 picometers plus 2 times what this number that we have over here for the Compton wavelength, which is 2.426 picometers. Okay, so when we put that value, we will get 14.9 picometers. So this is the maximum wavelength that the scattered X-rays can have. Okay? Find the maximum kinetic energy of the recoil electrons. So the maximum kinetic energy is equal to the difference between the energies of the incident and the scattered photons. Okay? So basically the maximum kinetic energy is equal to H times we said already we had the equation for the difference for the maximum kinetic energy. Okay? This is the energy. And if we're using the maximum kinetic energy, then we have to use a maximum change in the wavelength, right? Which we have found in part B. So where lambda dash is given in part B, this lambda dash will be 14.9 and the initial one was 10. So we will get H nu minus nu dash is equals to HC 1 minus lambda minus 1 over lambda dash, because nu, as we said before, nu is equals to C over lambda. ठीक है, और C को हमने कॉमन ले लिया है. ठीक है, C को हमने कॉमन ले लिया है, तो we will get 1 over HC times 1 over lambda minus 1 over lambda dash. And so we will insert the values now. Kinetic energy maximum is equals to H, which is the Planck's constant. ठीक है, 6.62 into 10 raised to power minus 34 joules second, times C, which is the speed of light, 3 into 10 raised to power 8 meters per second, divided by, we have to convert picometers, because here we're writing in picometers, ठीक है, तो हमें conversion factor भी इनको meters में convert करना है, तो they have written over here 10 power minus 12 meters per picometers. Because we have a wavelength in picometers, हमें इसको meters में convert करना है. So basically we have 1 over 10 picometers minus 1 over 14.9 picometers, because according to this equation, we have to insert the value of the 1 over lambda for the incident photon, and then minus 1 over lambda dash for the scattered photon. So here we have for the scattered and for the incident. Sorry? Someone said something? No? Okay. Okay, then we have over here 1 over 10.0 picometers minus 1 over 14.9 picometers. And so when we calculate this whole thing, we will get this value, which is equal to, if you convert this from joules to electron volts, you will get 40.8 kilo electron volts. So this is basically an example related to Compton effect. Now we have are there any questions related to Compton effect? We finished Compton effect, and we can go on to start X-ray diffraction, but I want to make some space for questions if anyone has anything related to Compton effect that they want to ask. You clear as सबको Compton effect? Okay, if there are no questions, then I think we can go on to do X-ray diffraction, ठीक है? So X-ray diffraction, according to the wave, what do we mean by X-ray diffraction? We'll be showing over here that X-rays, which are electromagnetic waves, obviously, they exhibit properties like diffraction. And I'll be showing you an apparatus here that will be used to show to produce the X-rays, okay? And then we'll be doing we'll be doing some calculations here as well. And I'll be doing an example, and we'll be showing, we'll be doing some theory as well as some calculations. So according to the wave theory of light waves leave a source with their energy spread out continuously through a wave pattern. So according to the wave theory of light waves leave a source with their energy spread out continuously. Basically जो हमारे पास wave theory होती है, ठीक है? We have wave theory of light and we have the quantum theory of light. The quantum theory of light is basically that the light is quantized. Basically, light is quantized in the sense that our photons, they have quanta of energy, ठीक है? Wave energy packets. So that's like the quantum theory of light is more like the particle theory of light. The wave theory of light is the opposite, ठीक है? So according to the wave theory, light waves leave a source with their energy spread out continuously through the wave pattern. So basically, according to the wave theory, the light waves, they have a continuous spread of energies. Okay? But according to the quantum theory, light consists of individual photons. Each of them, they have some amount of energy, a quantized amount of energy, like which is given by h times frequency, okay? And each of them has an energy small enough that can be absorbed by a single electron. Okay? Yet, despite the particle picture of light, the quantum theory needs the frequency of the light to describe the photon energy. Basically, the quantum theory requires that we know the frequency of the light, incoming light, to describe the photon energy. Because if we said that the photon, according to the quantum theory of light, photon energy is given by E is equals to hf, okay, where f is the frequency of the light. So we need the frequency to be able to describe the photon energy. So you can think of light as having a dual character. The wave theory and the quantum theory complement each other. Basically, we can think of light as having a dual character, okay? Dual nature. Basically, we have the wave theory and the quantum theory, and they both complement each other. But at any one time, the waves will either have a wave, will either exhibit wave properties or the particle properties. So now we talk about X-rays. Why are we interested in X-rays? Because X-rays, according to X-ray diffraction, they will X-ray diffraction, we will show the particle properties of waves. Okay? So basically, the photoelectric effect provides convincing evidence that photons of light can transfer energy to electrons. ठीक है? हमने photoelectric effect पहले पढ़ी थी, जिसमें हमने देखा था कि photons of light, they transfer energy to electrons. If you all remember, photoelectric effect is when we shine light onto a piece of metal, the metal will emit some electrons when the energy crosses the work function of the metal. So now there's an inverse process which we want to ask a question basically. Is the inverse process also possible? That is, can part or all of the kinetic energy of a moving electron be converted in a photon? We want to see whether the inverse process is also possible. Okay? Basically, like for example, if we have electrons coming to a piece of metal, like can that emit X-rays as well? So that's what we want to see. Okay? Can part or all of the kinetic energy of a moving electron be converted into a photon? So in 1895, Wilhelm Röntgen found that a highly penetrating radiation of unknown nature is produced when fast electrons impinge on matter. So basically, this is like the inverse of photoelectric effect. Basically, photoelectric effect में हमारे पास क्या था? Photoelectric effect में ये था ना कि हमारे पास light shine कर रही है on a piece of metal and the electrons are released, okay? But here we have something that's kind of like the reverse of X-ray, kind of like the reverse of photoelectric effect, where we have electrons are reaching a piece of metal based on this apparatus, where we have where we have a cathode here and an anode here, okay? And it's the cathode is negatively charged, the anode is positively charged. Then when we supply a voltage here, the electrons from here are going to be, we have a vacuum tube here, evacuated tube. The electrons will when they reach this this anode, basically X-rays are produced. So Röntgen, he was the one who discovered discovered that he discovered basically X-rays, but he discovered these X-rays, okay? And he found that, I don't know, wait a minute. He found that highly penetrating radiation is produced when he didn't discover the X-rays. I'm not sure if he discovered the X-rays or not, but he was the one who discovered that when X-rays, when fast electrons are reaching some piece of matter or some metal, for example, then X-rays, this really penetrating radiation, which is the X-rays, is produced. Not long after this discovery, it became clear that X-rays are electromagnetic waves. So later it became clear that X-rays were electromagnetic waves as well. So in 1912, a method was devised for measuring the wavelength of the X-rays, okay? So what we'll be doing in this X-ray diffraction is we will be using the diffraction, the condition for the constructive interference to figure out the X-ray wavelengths as well. To get the minimum X-ray radiation, etc. We'll see what we'll be doing here. So let me just go back to the slide. So a diffraction experiment has been recognized. Basically, we want to measure. 1912, a method was devised for measuring the wavelength of the X-rays. Basically, उस वक्त तक X-rays की wavelength determine नहीं हुई थी, ठीक है? So they used a diffraction experiment, which was used to figure out the wavelength of the X-rays. But as we recall from physical optics, spacing between adjacent lines on diffraction grating, basically, we will use the formula of diffraction. We will use this formula of diffraction, which is where, this formula, this condition for constructive interference, this will be used to find out the X-ray wavelengths, basically. And what basically this condition is only possible when we can only use the diffraction to figure out the wavelength of the incoming electromagnetic wave. If basically the spacing between the adjacent lines on a diffraction grating must be of the same order of magnitude as the wavelength of the light for satisfactory results. Basically, the diffraction grating must have such spacing between the adjacent lines must be of the same order of magnitude as the wavelength of the light, of the incoming light that we're using, okay? Of the light that is being produced when the electrons strike the piece of metal. Only then will we be able to get satisfactory results, okay? So, so basically, he used some crystals. Max von Laue realized that wavelength suggested that the wavelengths suggested for X-rays were comparable to the spacing between adjacent atoms in crystals. So basically, he used some crystals. Just say diffraction. We can use crystals can be used as a diffraction grating because, as we'll be seeing over here, they're like crystals. Where is it? Crystals are like this. For example, this is sodium chloride crystal, ठीक है? उसमें spacings होती हैं between the atoms, ठीक है? So it can be used as a diffraction grating. So we'll be talking about Bragg planes as well. So where were we? We were here, ठीक है? So electromagnetic radiation with wavelengths from about 0.01 to 10 nanometers falls into the category of X-rays. So basically, X-rays की जो wavelength range होती है वो 0.01 to 10 nanometers होती है, ठीक है? So we need to have a crystal. We need to use a crystal as a diffraction grating, जिसकी what do you mean? Is the spacing between the crystals, between the atoms in the crystal will be the same order of magnitude as this X-ray wavelength. Then only we'll be able to get satisfactory results. So the boundary of this category are not sharp. Okay, well, this diagram over here shows an X-ray tube, ठीक है? A cathode is heated by a filament. यहाँ पे हमारे पास एक filament है, ठीक है? Electric current is passed through the filament. The cathode is heated. It supplies energy to the electrons in the cathode, and the electrons are emitted by thermionic emission. The high potential difference is maintained. A high potential difference is maintained, ठीक है, between the cathode and basically we have electrons will be emitted from this cathode because of the heating that is being produced over here. The electrons will reach the anode. And then when they reach the anode, the face of the target is at an angle relative to the electron beam, and the X-rays that leave the target pass the side of the tube, ठीक है? So what's happening over here is that electrons are reaching the anode. When they strike the metal, some X-rays will be produced. So basically, what we have here. The X-ray spectra that results when tungsten and particular molybdenum targets are bombarded by electrons. So basically, they did some experiment. These scientists did some experiment with two metals. One is the tungsten and one is molybdenum. Molybdenum, ठीक है? It's a particular kind of a metal, or crystal, and what we're doing here is that we're bombarding electrons to these two different targets at several voltages. We're just applying different voltages to that. So in the case of molybdenum, intensity peaks that indicate the enhanced production of X-rays at certain wavelengths. Basically, our X-ray spectra that we get when we when we use this experimental setup for two different materials, two different targets, are produced like this. X-ray spectrum of tungsten at various accelerating potentials. We have the tungsten target, and at different potentials. We apply a different voltage here, different voltage here, different voltage here, different voltage. We get like some peaks. And this is for the at a particular voltage. This one is 35 kilovolts, kilovolts for the voltage, and we get a peak. This is for the tungsten, and this is for molybdenum. Now, how can we understand these? In the case of molybdenum, intensity peaks occur that indicate the enhanced production of X-rays at certain wavelengths. As you can see, there's some peaks in this molybdenum here, some peaks. What does that correspond to? These peaks occur at certain wavelengths for each target material. This phenomena will be discussed. Basically, what we're saying here is that there's something known as this is going to be telling you about the maximum of the X-rays diffraction. These peaks tell you the maximum of the X-ray diffraction, because when X-rays are produced, they strike a target. Then we will get some diffraction because of the crystals that are there. The target crystals, they will have some spacing between their atoms, and because of that, there will be some diffraction of the X-rays. So wait a minute, let me just see where that was. Yeah, so the X-rays produced at a given accelerating potential vary in wavelength, but none has a wavelength shorter than a certain value, lambda minimum. So basically, the X-rays that are produced at a certain accelerating potential, as you can see over here, at any given potential, there's a minimum wavelength at which the X-rays are being produced, and that minimum, no X-rays will be produced if the accelerating potential at a lower than a given wavelength. They will have a range of wavelengths, but below a given wavelength, no X-rays will be produced. So we want to figure out what this lambda minimum value is. This lambda minimum value over here for these particular voltages, there will be a lambda minimum. The X-rays produced at a given accelerating potential V vary in wavelength, but none has a wavelength shorter than a certain value lambda min. So increasing V, the potential decreases lambda min. As you can see, if you are increasing the voltage, the lambda minimum decreases. That means the lambda minimum is becoming smaller and smaller. So lambda min is the same for both tungsten and molybdenum targets. As you can see over here, at a given voltage, the lambda minimum is the same for both the tungsten and the molybdenum. These are two scientists, Duane and Hunt. They found experimentally that lambda minimum is inversely proportional to the voltage, and the relation between the lambda minimum and the voltage is given by this formula, where lambda minimum is equals to 1.24 times 10 raised to power minus 6 divided by the voltage. And this is obviously in volts dot meter, where because the voltage will be in volts, right? So that voltage and voltage will cancel, you will get it in meters. So that will be lambda minimum. So lambda minimum will be given by this formula, where it's inversely proportional. The wavelength is inversely proportional. The minimum wavelength is inversely proportional to the voltage that is being applied, the accelerating voltage that is applied, accelerating potential. And it's given by this 1.24 times 10 raised to power minus 6 volts meters is the proportionality, inverse proportionality constant. So yeah, I think we've gone out of time, but I hope that we will continue from like slide number 33 and we have to finish up till slide number 48. ठीक है? आज हमने कितने slides किए हैं? 33, and we did from Compton Effect. We did from 14 till 33, so we did almost like 20. And then tomorrow we'll do from 33 से लेके 40, 49, 48. So I hope that we'll be able to finish everything by tomorrow. ठीक है? Are there any questions? Let me download the attendance list. आज कम students आए हैं class में. ठीक है? So we have a quiz on Wednesday, by the way. I hope you all remember. ठीक है? And our quiz will be on Wednesday, which is on nuclear transformations topic. And next week, we'll be finished by tomorrow. And then we have a quiz on 23rd. And I don't think we'll be able to have a 7th quiz because I have to enter everything by 28th. ठीक है? I have to enter everything, all the marks, sessional marks, and all the attendances by the 28th. And then the last week, which is this week, will be all of you to study for the final exams. ठीक है? And which is the final exam is, I think, on 8th of January. ठीक है? And the paper pattern, the final exam is going to be a closed book exam, as with all quizzes and final exams that we've been having in the previous semesters. ठीक है? Especially last semester, which was online. ठीक है? We'll be having similar type of paper pattern. It will be closed book exam. And it will consist of questions, with each question can have a few parts, and yeah, basically that's all. ठीक है?
लेंथी ना बनाइएगा.
लेंथी ना बनाए? ओके ठीक है. अभी या ओके.
मैम लास्ट टाइम वाला बहुत लेंथी था.
एस्ट्रोनॉमी एस्ट्रोफिजिक्स लेंथी था?
जी मैम.
Yes, ma'am.
ओके, I'll see. Spherical astronomy का इतना लेंथी नहीं था वो वाला previous सबसे पहले वाला. Okay, I'll see what to do. Okay, I haven't made the exam yet, but I'm going to make it soon. ठीक है?
Okay.
Okay, so I guess that's all from my side for today, and we will continue tomorrow. We will continue with X-ray diffraction, and hopefully with we'll just have to finish all these slides by tomorrow. Okay, so that's all from my side. And so no one has any questions, right? Okay, then Allah Hafiz.
Allah Hafiz, ma'am.
Allah Hafiz.